Hello, everyone. Thank you for joining today's CelerData webinar. Today's topic is on customer-facing analytics and how to choose a real-time cloud data warehouse for this kind of workload. Sorry, that was my cat. My name is Sida Shen. I'm a product and product marketing manager at CelerData. Thank you everybody for joining. So now let's get started. So yeah, before we actually start, I actually want to talk about like why I wanted to do this topic. CelerData, we're a database company, right? Like the most deal we actually win are not surprisingly not like just one-on-one, like head-to-head POCs. Most of the deals we win are actually like the best deals are people using a great solution for a wrong kind of workload, right? So today's webinar, I really want you guys to take home, like how to get customer facing analytics, this kind of, data infrastructure right in one go, right? Okay, let's get started. So first, let's talk about the agenda. Also, you have question, please feel free to directly ask in the chat, or even better, use the Q&A function. We're gonna have enough time to take care of everybody's question at the end. So first, we're gonna talk about customer-facing analytics requirements and challenges, unique challenges. And then we're gonna talk about what to look for when choosing a cloud data warehouse for this kind of workload, right? We're gonna talk about the features and capabilities, that enable you to run joins at scale, to run real-time updates, and to run everything at a scale, right? And then we're gonna take all of those and compare CelerData Cloud with ClickHouse Cloud, right? We're gonna do a architectural comparison, see the trade-offs, and we're gonna do a demo to run a few queries on a quite large data set. And we're gonna see a lot of cool things. And then we're gonna see, from what we learned today, which is good, for what kind of workload, right? So first, customer-facing analytics requirements, right? Customer-facing analytics is basically the process of, directly serving analytics to your end users, right? So for example, on the right, you have, this is the YouTube Studio page, actually one of my videos. You can see like the real-time views and watch time and subscribers and everything there, right? And right there is customer-facing analytics. I'm the customer and this is analytics, right? And typically this kind of workload is very high stake, right? Is a lot of the time is the company's revenue driver. It is part of their product. It is part of their competitive edge, right? And customer-facing analytics is really everywhere, right? From external-facing advertisement dashboards, like one of our users, Pinterest, that use us CelerData to power their advertisement dashboards direct to the advertiser, so the advertiser can see all the campaign performance in real time, so they can tune everything in real time, right? And in product analytics, CelerData, our product has been really used a lot, directly powering the product. For example, account-based marketing, right? And that's one of the marketing attack. That's one of the great use case. A lot of like complex kind of logic, right? And then you have to another extreme, right? Complex process mining logic, right? And then that's very, very a lot of very deep and complex kind of business logic, right? And sometimes we see like 50 table join in one query, right? So it's a very diverse kind of workload that is basically everywhere, right? So the technical requirements of customer-facing analytics, this is our experience, seeing all of the users running this in the field. First is it's always relational schema and multi-table queries, right? So either, so you always have many tables in terms of, instead of just one, right? Like observability, right? And there are always, updates and deletes come up a lot more often than you think, right? And a lot of the time it's real time, right? And then a lot of them are multi-tenant, right? So we have to be able to handle very heavily skewed data from different clients, from our users, right? Sometimes, the biggest client, like they have like 100 clients, and their biggest client can take up like 30% of their entire data volume, right? And also the governance, resource isolation, individual scaling is very important, for this kind of use case. And for query, and this really largely depends on the use case, right? And in general, for a lot of the customer-facing dashboards, like we look at sub-second query latency, thousands or tens of thousands of QPS, and sometimes the queries are not as complex, right? So it's really scan heavy, scan bottleneck, and a lot of fact and small dimension table join with very simple aggregations, right? And for this kind of dashboards, after filters, not that many rows left, and the queries are quite simple, but still multi-table, right? So run everything in sub-second and very high concurrency. And then we have those kind of in-product analytics kind of customer-facing use cases, right? So this is a lot of product kind of logic in it, right? So it's a little more complex. So typically with this kind of workload, we see hundreds of QPS and higher cardinality aggregations. So more complex aggregations with distributed fact table join very big dimension table, or fact table join fact table, right? Actual distributed join, right? And also, AI agents, we already have a few users that are in production already. We actually have a webinar later this month talking about one of our users. Go check that out and register. And those are some of the most unoptimized random queries I've ever seen in my life, right? So we have to be able to handle those too, right? So this is customer facing. Some of the technical requirements we see in the field. And then the challenges, right? So first is the join versus denormalization challenge, right? So you have normalization, basically it's going from one big flat table that has all of the data, basically inner join of all of the tables, to a star or snowflake like multi-table schema, right? It's normalization, and the other way around is denormalization, where you have a relational schema and you basically do an inner join of all of those and come up with a big flat white table. Right, normalization is good, right? And normalization has been a relational database. It's been around for 40 years, right? It's there for a reason, right? It eliminates redundant data, really compress your data. It simplifies the query process, right? Improve your workflow, and it's really cost efficient, right? But a lot of the especially real-time data warehouses, they're not optimized for joins, right? So that really forced a lot of data practitioners. So you guys are forced to build really complex pre-processing pipelines, right? And that's really a pain, especially when their requirements are real-time. Like you need good data freshness. Let's say even in the minutes, right? It's something like Spark is not really gonna cut it. It's not really gonna be able to catch up. You need to do stream processing, right? And that's very difficult to do, right? And what we see is a lot of the team just give up on data freshness because of their engine cannot do join at scale. And that's astonishing. I think this is the biggest roadblock for teams to go actual like real-time analytics. This is the biggest bottleneck we see in the field. And also, not only makes the entire pipeline very expensive, it actually makes schema evolution very expensive as well, right? So, for example, you see here you have a dimension table, right? This is a customer table, right? And this is small, let's say 100 rows, right? And you have a fact table on the right, say order table, let's say a trillion, right? Just for the fun of it, right? Because and you want to serve some kind of dashboard, and because your underlying database doesn't support join or doesn't do that fast enough, right? You end up denormalizing, right? Into putting all of the columns into that one big table with a trillion rows, right? And that works. You don't have to do the join, although it takes a lot of space, but it works, right? But what if one day you want to like change a column, right? You want to rewrite your customer name, you want to mask the entire field, right? If you don't denormalize, you only have to change 100 columns. But if it's denormalized, not only you have to change this, you have to change the entire trillion rows on this table too. Right? This is data backfilling, and this is painfully expensive and slow. And this denormalization process locks your data into a single view format. That's basically no flexibility to really do anything, right? We have a user that runs a metrics platform, and before they were doing denormalization, just like this, right? So every schema change would take like days, hours, hide hours into days, to complete. And that's just not acceptable, for a metrics platform to not be able to do a schema change, not be able to add a new feature or metric, right? And this is denormalization and versus join. And another challenge we see is really with the upserts and deletes, right? And the upserts and deletes is a very difficult problem to solve in OLAP, because OLAP, we use columnar files to have better scan performance, right? And real-time updates and deletes is a very hard problem for OLAP system, especially if you want to do it in real time. And current solutions are far from perfect. So first you have like read optimized kind of format, like copy on write, basically write a file, right? And write a new file, delete the previous file, right? Replace. And this is not really, real time, right? You cannot really get really low in the minutes, even low in the minutes or high in the seconds, kind of data freshness. And you have write optimized formats, right? Such as merge on read. And basically you write into different versions, and there's a backend compression compaction job that merge all of the versions together, right, in the backend. And the fact is that really affects query performance. First, that compaction never catch up and use a lot of resource. That's one. And second, that multiple version actually prevents a lot of filter to push down to the storage layer. So you actually end up scanning a lot more data than you would have if it's just not a merge on read still updating table, right? So this really affects your query performance. Not only make it very slow, but also make it very unpredictable, right? Sometimes like even 10 times slower, right? So this is a challenge of data upserts in OLAP, right? And now we are going to talk about how to solve these problems one by one, right? So when you want to achieve these kind of requirements, what kind of features or architecture should you look for, right? What is the state of the art? So first, we talk about joins, how to do on-the-fly joins. So let's break that down, right? So let's first talk about a life of a SQL, right? So what happens, when a SQL actually hits a database, and what do we do there, right? So first it hits a networking layer, and then it goes into a planner, and the planner generates a plan, right? A physical distributed plan or a single node plan, or a physical plan, right? And that goes into the execution layer, right? The engine scans the storage and then does the execution, right? So we're gonna take a look at each part and how that affects join performance, right? So first is query planning, right? Query planning is such a difficult problem because there's so many combinations of ways you can run a join query, right? And the number of join orders grows factorially, with the number of table you have, right? And that's very important because if you join the wrong way, you really explodes your memory. If you build the hash table on the wrong side, that's really bad. We're gonna see in the demo in a little bit, right? And also you have to choose, physical join algorithm, right? So what kind of algorithm do you use? Do you just hash join everything, or you merge or whatever, right? Physical join algorithm you have to choose, and distributed join strategy, right? Do you want to do a broadcast join, or you want to do a shuffle join? That is, you have to choose that too, right? And also with runtime filters, in everything, right? And the wrong plan can result in a several magnitudes of difference in performance and cost, right? It's so incredible. All of those rule-based optimizers still have a job. If I make a mistake that costs this much money, I'll be out of the job in like 10 seconds. And what are the optimizers, right? So in the industry, basically we have two kinds. First, it's a rule-based optimization, and then it's a cost-based optimization, right? So for rule-based optimization, it basically makes decision based on the set of predefined rules, right? And there is no consideration for the actual data distribution or sorry, I think, is there anything wrong with my microphone? Okay, no, sorry. Okay, there's no actual like consideration for your data distribution or the statistic or anything of your table, right? It works for simple use cases, especially single table kind of scenario, but for complex join queries, it just doesn't work, right? But it's easy to implement. And then we have cost-based optimizer, and this is a state of the art kind of approach for join queries. So what it does is, take a look at your data and collect statistic periodically and estimate the cost of each candidate plan, and basically select the best one based on the calculated cost, right? So it's actually based on the actual real-time statistic of your data, right? So this is the most accurate way to basically to come up with the most optimized plan, the best ever, right? But this is like really difficult to write. But cost-based optimization is what you are going to want to look for, when you want this, optimized query plan, for your join queries, right? And then after a plan is generated, right, now it's time to actually do the computation, right? And there are different ways, different compute architectures on a higher level, right? So there's scatter-gather kind, they're MapReduce or stage-by-stage kind, and they're MPP. I'm going to go through each one of them one by one, right? So for scatter-gather kind, these are simpler kind of architectures that don't really have a general purpose, shuffle or exchange node, right? So whatever the data distributed is that you cannot change it, you cannot redistribute the data during the query process, right? So shuffle join doesn't work, right? You have to broadcast join, basically copy all of your small table and broadcast to all of the nodes, right? It requires a very small left table, right? Or you can do a co-located join, right? So basically require data redistribution by a join key, right? So this really works only if you have big join very small, or you have pre-shard, you have your data pre-distributed by the key you're going to join it with for fact-to-fact join, right? Or other, it's not going to work. But this is a very simple and robust kind of architecture for your single table queries. But for joins, there's a lot of limitations here, right? One example of this is open source ClickHouse. And the next one is like MapReduce kind, or stage by stage computation, right? It does have like shuffle and sort, but everything is materialized to disk every time it does the data shuffling, right? And their wait time, between every stage, because it needs to persist on stage, on the disk, right? The reason why it persists on this is definitely not to slow it down purposely, but is to, to be optimized for those like long running ETL jobs. When it fails, you can start like halfway instead of all the way from the beginning, right? It's very good for like long running batch jobs, and not those like interactive kind of query or low latency, high concurrency type queries. One example is Spark, right? It's a great tool, for use for like pre-processing or ETL kind of job. And the last, not least, is MPP, massively parallel processing type compute architecture, right? So this does have data shuffling, and it shuffles between the nodes memory. So it's really optimized for low latency, high concurrency type of join. And also because it shuffles, so you can scale your joins to as many nodes as you want, right? With all of the tables as big as you want, right? So no really any kind of limitations there. So this is a distributed compute architecture, right? And okay, so this is how you do join and at a scale, and also how do you do that with low latency and high concurrency? How to be optimized for performance, right? Columnar storage and fully vectorized operators, right? So think of when you want to run a aggregated query, it's always by column, right? So this is why most OLAP solutions, we store everything in the columnar-wise fashion, because this is great. This is good for the type of scanning that we do, right? So it's column by column, right? By saying fully vectorized or vectorized operation, it's basically when you do run the query in memory, you also run them in batches, right? That's the same reason, why we do columnar storage, just to process things in batch. The more batch you run, the faster your OLAP query is gonna go, right? So columnar storage and vectorized operators. And to add to that, SIMD optimization, right? You are going to want to find a database or OLAP database, at least the execution layer is written in a lower level language that can take advantage of SIMD optimizations, right? So basically for every instruction cycle, right, you are able to process a batch of data instead of just one point, right? So makes everything run so much faster. And CelerData, we implemented this. So the implementation, the fully vectorized operator by operator, we see around 3 to 15 times of performance gain just from this alone, right? And also, we have to do everything by scale, right? But scale is a multi-dimensional kind of problem. Just because your cloud data warehouse has that auto scaling button, it doesn't mean that it can actually scale everything, right? So first you have to consider, how do you scale without moving data, right? How do you scale instantly without actually like touching storage, right? So you want to find something that's compute storage separate, right? So you want to find something that has external storage, like an object storage, like AWS S3 to persist data, and compute separated, so you can scale each one of the compute separately, right? And you are going to want to scale all operators, including join queries, right? You want to find something that has an MPP or massively parallel processing kind of architecture, right? And a lot of the customer-facing use cases are multi-tenant, right? You want workload isolation. You want compute separation to make sure all of your tenants have the appropriate amount of resources to run, the kind of workload they need to achieve the SLAs, right? And also you want to find something, that can horizontally scale each one of the compute, right? And okay, so this is how do we achieve this? Real-time offsets. Forgot about that. How to achieve real-time offsets, right? So we talk about copy on write and merge on read, right? And there is a new kind of way to do this, right? It's basically to have a row level in-memory index to accelerate the process of the merge process, right? So basically what you do is you do a mark delete during data ingestion, and you filter at query time, right? And then there is an in-memory row level primary key index that accelerates the mark deletes. It basically, store the hash of your primary key columns and map that to wherever that thing is stored on disk. So you can find whichever location needs to be deleted in O1 time, right? So there is no like merge operation because everything is taken care of at write time. So best possible query performance. And second level data upserts directly on your columnar storage without actually affecting query performance. And it's fraction of the storage when compared to other solutions, that actually require a complete row storage on the side of the columnar storage. Okay, so now we take a look at CelerData Cloud and ClickHouse Cloud and apply what we learned today. So ClickHouse Cloud, this is the architecture, right? So first, it features a storage and compute separation, right? So it's able to scale without moving your data, right? And they have replicas. Replicas is how ClickHouse Cloud scales its concurrency, right? So each replica is a Kubernetes pod, right? You're able to scale up and down. So it's a single instance compute replica, right? So think of every compute replica like a DuckDB, right? And you can spawn multiple replicas, to scale your concurrency, right? And query only runs in one replica at a time. So there is only so much room, you can scale one query, right? Scale the query latency, right? But they also have a feature that's called parallel replica, that very simple queries can run across replicas, but it is not on by default, and it has a bunch of limitations. Only works for single table queries with no CTEs, with no subqueries, right? And it features, automatic vertical scaling of their replicas, right? Only vertical scaling because it's one node, one instance. And this is CelerData Cloud, right? Also storage and compute separation. And how it scales is very different, right? So instead of replicas that only has one node, CelerData Cloud has multiple compute warehouses. And each compute warehouses has bunch of instances in it. You can scale horizontally, right? Also automatically, right? Okay, so these are the two solutions we're going to take a look at today. And then we're going to run a very short demo. This is on the SSB dataset. This is on the SSB multi-table schema dataset. So it has a fact table that's line order, 6 billion rows, right? And a larger dimension table that has 30 million rows and a bunch of smaller, even smaller dimension tables, right? So this is a classic kind of, external facing, like dashboard kind of profile, right? Okay, so let's take a look. Okay, so this is CelerData Cloud, right? We have the SSB table and we have everything here, right? And this is SSB 3.2. And this is a warehouse view. You can scale auto scaling policy here. And okay, let's run this query with 4 tables, with the biggest fact table and the big dimension table and 2 smaller dimension tables. Right, let's run this again. We have no result cache, by the way. This runs, right? And then I issued another query, the same exact query I copy pasted from here to here. ClickHouse. OM'd. Now let's try to figure out why, right? So let's take a look at the query profile of the CelerData Cloud side, and let's see if we can try to solve this for ClickHouse, right? So okay, so what it did is it scanned the line order table, the biggest table, and first, although it is not the first table here, so we did a join reordering, right? Let's look at what order we actually, CelerData Cloud actually ran this this query in, right? So this is line order, join supplier, join customer, and join dates, right? Let's reorder this for them. Customer, line order. Wait, which is the next, the second one? Let's see. Line order, supplier, customer, supplier, customer, dates. Oh, perfect. Now let's run this again. It's not using memory now. That's good. Okay, I didn't prep anything to say when it's running. Okay, we see it's going to run. So when you have joins not ordered correctly, if you want to build hash table on a wrong table, you have gigantic intermediate results. It's going to crash any system you have. It's going to use all of the memory you have. So this is, yeah, how much optimizer plays a part in this, right? So when you use ClickHouse, you have to either, even it's correct, it ran for 40 seconds, right? You have to manually tune your query one by one. Okay, so what do user do, right? So this is too painful, right? What do user do? They do this, right? So they do a denormalized table. So here I actually created another table here called line order flat. Basically, this is the inner join between customer, line order, parts, and supplier, right? Okay, so let's see how big this is. Line order flat versus line order, around 3 times the difference, right? So here is 3 times, but actually in production, we see around 10 times storage growth when you denormalize. Very, very expensive to do. And because SSB is kind of lower cardinality, ClickHouse is really good at compressing data. So it doesn't look that bad here, but in production it's around 10 times different, right? So after doing that, you can run the flat query, right? So this is the same thing. Okay, I don't think the data is cached. I'll give it another chance to run it hot. And this is another problem with only having one instance. The scan really becomes a bottleneck if your data is not like sorted or like sorted on like the filter. Okay, same exact result. I'll run it again when the data is hot, when the cache is filled. So it should be faster this time. Okay, yeah. So this is what you get, right? Um, yeah. So a lot of explosion on the disk. And if you want to, let's say, change something on the dates, right, or on the parts, one column, you have to rewrite every single row in this table as well. 6 billion rows. Not exactly too much fun, right? Okay, let's come back. So that was a demo, right? And still conclude what happened, right? So query optimization, query planning didn't work on ClickHouse because it has a rule-based optimizer, right? So it didn't know how to reorder the data, reorder the tables because it doesn't know how many rows exactly are in each table and how the data is distributed, right? Yeah, so query optimizer, CelerData Cloud is cost-based and ClickHouse Cloud is rule-based. And vectorization CMD, actually, both of them are really optimized for low latency, high concurrency type of um, OLAP style query, right? And multi-table queries, CelerData Cloud runs them distributedly because it's MPP architecture. And ClickHouse Cloud, this is a brilliant design because it only runs in single node. So every replica has a single Kubernetes pod. So every multi-table query you run in ClickHouse is going to be a single instance join, a single instance kind of query, right? And scale for concurrency, CelerData Cloud is designed to scale. You can scale through scaling each one of the warehouses horizontally or adding additional warehouses, right? And for ClickHouse Cloud, you can vertically scale replica, but that's up to, I think, 89 vCPUs. And the better way is to add more replicas to scale for concurrency, right? So let's conclude a little bit, right? So technical use cases for Cellular Cloud and ClickHouse Cloud, right? Thousands of concurrency, low latency. For both of them, I'm going to say yes on single table queries, right? For join, CelerData Cloud is built to perform any join at any scale, right? ClickHouse Cloud, on the other hand, is for very simple joins and prepare to write hints in terms of how to run the query distributedly. Oh, it doesn't even do distributedly, and how to order the table, right? And also the join needs to fit within one pod, right? If you scale to the top and latency is still not working, you probably need to denormalize, right? And for real-time ingest, both of them I would say yes, second level data freshness, but when there's upsert involved, ClickHouse Cloud still relies on merge on read, and that's going to affect its query performance, right? And for ClickHouse Cloud, the best kind of use case is low latency, high concurrency workloads with single table, low cardinality, append-only kind of data, right? So observability, they're absolutely the king of observability for any kind of OLAP databases, right? And also you can use CelerData Cloud, for sub-second high concurrency with any kind of data models, single table or multi-tables, scale, and different any kind of cardinality, and also mutable or append-only kind of data, anything you want, right? It's great for customer-facing analytics for all of the use cases we talked about in the second slide before. Okay, so there is an example. One of our user Demandbase, they were using ClickHouse. It's account-based go-to-market platform, for B2B enterprises. So basically what it does is you have a bunch of leads, right? You have a bunch of prospects, and Demandbase can help you score those prospects in terms of how much interest they have in you, right? So a lot of business logic. They were powering their customer-facing workloads on ClickHouse, and they encountered a lot of challenges, right? So first, we talk about data becoming a single view format, very difficult to do a schema change. And also, denormalization 10 times their storage, right? And also the denormalization pipeline added a lot of overhead to a point that real-time analytics just became impractical for them to do. And then they found CelerData Cloud, powered by Starbucks, and they really greatly reduced the need for denormalization, right? So avoiding the storage and compute bloat of the join limitations, the denormalization pipelines, and greatly simplified their architecture. Now they run most of their queries just on the original schema, right? So now they actually can go real time because they don't have all of the pre-processing denormalization pipelines there. And more flexible schema evolution without the massive data backfilling every single time they want to change a column or do anything. Okay, and also AI agents are coming, right? We're serving end users, and today and tomorrow, actually today, we're serving AI agents, right? Then the ask from LLMs are actually quite similar, to a lot of the customer-facing kind of workloads, right? Query at AI scale, sustain thousands of concurrent agents, querying without performance degradation. You have to be able to scale concurrently, right? And sub-second kind of analytical insight. You want to deliver instant, reliable query responses, to keep up with the AI reasoning. It does work a lot faster than human, right? And you have to be ready for any kind of query, right? Be able to handle all kinds of crazy, unoptimized query, multi-table, 10-table kind of query that LM throw at you, right? And also your engine needs to be self-optimizing, right? Smart query planning becomes even more important, right? And automated performance tuning and adaptive query optimization without a human in the loop. Okay, so serve your real-time analytics for end users and AI agents. If this sounds interesting to you, you can sign up CelerData Cloud using this link to get a 30-day free trial, and join the Slack channel of our open source community if you're not really ready for a POC yet, to join the 5,500 people, talking about real-time analytics, customer-facing analytics, and AI agents. Thank you. That's all I have. Let's take a look. Do we have any questions? Okay, we do have some questions here. Let's take care of the chat first. We're only seeing ClickHouse. Sorry. How long did CelerData Cloud run? That was 2.5 seconds hot. Everything was already in the disk cache. Without cache code, it's like 10 seconds. And the ClickHouse Cloud code was like 40 seconds because of the scan. It only has one node. It's difficult. Will ClickHouse not use more pods for Upserts if those nodes have shared data for Upserts? Yeah, it helps. When it's actually ingesting, it does use more pods, meaning more replicas, right? Does CelerData Cloud run on AWS or some other platform? Yes, it is on AWS, and it is BYOC, so bring your own cloud. Yeah, so basically the CelerData Cloud, the database is deployed in your AWS account, and we have a remote kind of management a layer that does the maintenance remotely. So how much does CelerData depend on quality of data modeling? If you mean by needing to pre-process or denormalize, not really, because CelerData is designed to run joins. What was the architecture used to present CelerData? It was shared data. Shared data is the elastic cluster. And Q&A, can I download your slides? Yes. Why are you still using MapReduce? Because MapReduce is a type of, it's MapReduce stage by stage, is the same thing, right? It's a similar kind of architecture, right, evolved. Those are for like ETL type of workloads. Does have you tried vibe coding CelerData? Yes, yes and no, right? It's very difficult, for a complex system like CelerData's core. For the database, it's very difficult because the core Starrocks, the code is just a lot of that. The context is very long. It's still a little difficult for LLM to do, but we do leverage AI. How would you compare ClickHouse Cloud and CelerData Cloud for observability type of use case? Mm, I would say ClickHouse is very, very good. And a lot of the capability really depends on it's really, I mean, the capabilities are quite similar. If not, ClickHouse is better in some. For observability, I would say it's close, but I wouldn't even say we're better. I'm honest. How degrade execution when using LLM? Oh, when LLM generates SQL, how much performance degradation? We do see very, very unoptimized queries. A lot of them. That really depends on like how well our optimizer can handle that. If it cannot generate good plan, then it's bad. Uh, it's really case by case. Can AI simplify your processing? Pre-processing, there are a lot of projects out there, even open source ones, that automates your data pipeline. There's one company called, I think, what is the name? They do like automatic DBT, and a lot of other projects that really focus on SQL. There are many projects that do this. Do you propose this CelerData can replace Spark or not? Okay, so for some use cases, I've seen CelerData Cloud actually replace Spark with this materialized view, um, because it's a different like compute architecture, right? So Spark is really like for like hours long, and you break the job break, you can start like halfway, right? And CelerData Cloud is more still MPP. We have operator spilling, basically splitting to disk based on operator by operator, right? So to increase stability for long running jobs, that takes a lot of memory, right? Um, um, I would say for yes, I've seen terabytes or tens of terabytes of kind of job done in materialized views. I have seen a user just yesterday, it has 3,000 materialized views. And that's basically would have been running in Spark clusters as all like pre-processing. Is the performance seen on CelerData Cloud be the same with on-prem setup? Um, we don't really run an on-prem CelerData if you're talking about the Saros project, which the CelerData Cloud is based on, right? The core performance is the same. So yes, if the hardware given is all AWS and it's the same, you should expect the performance to be similar as well. Okay, this is all of the questions we have. Anything else? We're at 50 minutes. Okay. Thank you everybody for joining today's webinar. That was a lot of fun doing a demo. Um, thank you so much. Give you 10 minutes back. And thank you guys, and see you again next time. Thank you. Appreciate that.